All right, so I'm in the folder week 4 folder. But by the way, don't forget to work on this essay 1. You turn it in over here under essays. Make sure you do that. All right, so this is of course the homework 6. The first homework. There's also a homework 7 dealing with magnetism. All right, so notice I have this thing called circuit breaker example and then series and parallel circuits. Let me open series and parallel circuits first, and oops, open the wrong one. Here it is. So this is just the definition. In a series circuit, the current is the same for each electrical device. In a parallel circuit, the voltage is the same for each electric device. And let me just show you that very specifically. Okay, so here's a battery. So here's an example of a battery. Remember the top line there, this is the positive side, this is the negative side. You don't really draw that, that's implied. And let's say, that didn't come out at all, did it? Let's say that we have one electrical device. Alright, and we'll call that R1. And let's say it's connected to another electrical device. We'll call that one R2. And there's even a third electrical device right here. We'll call that R3. And so the idea, this is series. Of course, this is a series circuit. Series. And why is that series? Well, if the current, which comes out of the positive side, we know it doesn't actually do that, goes through this resistor, goes through this resistor, or actually more generally I should say, goes through this electrical device, goes through this electrical device, and goes through the third, and then comes back to the other side of the battery, or the power supply, the DC power supply. This is, of course, DC. Then whatever current comes in this side has to go out that side, and whatever current comes in this side of this electrical device has to go out that side. There's no other path for current to travel, and that's why we call this a series circuit. Okay, the parallel circuit looks a little different, and we can have a battery again, just a plain old battery. I'm just going to write two or draw two of these. So this is the positive side. Again, you don't normally draw that. I don't know why I'm putting plus and minus. So this is a battery, and here is our first resistance, or our, I should say, electrical device. I'll call this R1, and let's say there is a second electrical device. I'll call that one R2, and this is already parallel. Okay, I'll put another one. I mean, you can have as many devices as you want in parallel here. So here's R3, and just to make it interesting, we'll put one more electrical device. We'll call that R4. All right, and so just what's making this parallel? Of course, it's the positions of all these electrical devices, and go back to the definition of a parallel circuit. Oops, which we're about to get to. The voltage is the same for all the electrical devices. All right, and so if you take a look at that, see, here's whatever the voltage is of this battery. Let's say it's 30 volts. I mean, it could be anything, but I'm just making that up. Then that 30 volts, notice, is felt across this resistor, and it's felt across this resistor, R2, and it's felt across R3, and it's felt across R4. Whether they're resistors or it doesn't really matter, they're electrical devices. And so the voltage is the same. And we can use this information to solve circuit problems. And just like we could use, although we're not going to get into this, for series circuits, you could say, well, the total resistance is the sum of R1 plus R2 plus R3, And then if you knew this voltage over here, you could figure out the total current, because the total current goes through each one of the resistances or devices. And I keep mixing those up. All right, so let's take a look at our. I probably shouldn't have put 30 volts there. Hold on, let me pause. All right, so I redrew this a little bit. I don't know that it's any better, but let's actually look at this example, because there's actually 4 electric devices. You can count them. Whoops, let's start at the beginning. It says a circuit with 4 devices connected in parallel, so we know right away when it says parallel, that means that it's the same voltage, and they give us the voltage. The voltage is 145 volts. I'm going to draw that on our right here. So the voltage is 145, and that's going to be true. And we're going to put a V in there. So that's going to be true for each electric device. All right. So I realized I had to change this this device number 1. So we have these 4 devices. The first one is an electric iron, and they give us the resistance. Okay, so I just changed it so that it's now. How do I know it's resistance? It's because it has the symbol ohm. All right, and so let's write that in there for R1. So now we know R1 is 45 ohms. All right, and for the second device, they don't give us the resistance. Notice B, it says a 2 kilowatt toaster. All right, so here let's think about that. So that's R2. So I'm gonna write that as, that's actually power 2. All right, so power 2 is what was it? 2 kilowatts. 2 kilowatts. And device 3, we got to look back and see what it is. I'm going to stop doing this. All right, so device 3 is 400 watt light bulbs. 400 watt light bulbs. So, so they gave us the power of device 3. So even though it's 4 of them, we can get the total power by just saying, 4 times 100 watts, which is of course just simply 400. That's 4 watts. And then power 4. They don't give us in watts. If I remember correctly, I think it's in horsepower. So there it is. It's 1.3 horsepower. If all the devices are turned on at the same time, will this trip what's called a circuit breaker or a fuse, which happens to be 25 amps. All right, let me explain that. I got to go back to the circuit. All right, so let me write in the power here. So the power is, what was it, 1.32 HP. And of course, we're going to have to change this. We know that 1 HP, I'll just start doing this right now, is 746 watts, because we need this to be in watts, not horsepower. You can't do the calculation with horsepower. Here, we might as well. So 1.32 times 746 is 984.7. So this last device is 984.7 watts. All right, so that everything's in the, well, except for power 2. This is 2 kilowatts, which of course is 2 times 10 to the third, 2 times 10 to the third watts, which is of course simply 2,000 watts. All right, so we know the power for device 1. We know the resistance, and we've been told that there's this device, and I'm going to draw it like this. It's a little squiggly line right here. That's supposed to represent a fuse, and that fuse is rated at, let me read the problem again. I think it was 25, right? 25 amps. All right, yeah. So what that is, the fuse, or so this is a fuse or a circuit breaker. This is a So this is a fuse or circuit breaker, is rated at 25 amps. Did I say watts? I shouldn't have said watts. Anyhow, what is that? What is it doing? Okay, so if the total current that comes out of this power supply goes over 25, what's going to happen is that fuse it basically opens up and it shuts off the rest of the circuit. If fuses actually, the way you talk about them is they blow, the fuse blows when it opens up. They're kind of a pain. If you have fuses, you have fuses usually in a car, for example, and you have to actually replace the fuse. What's nice about a circuit breaker, and so in this example we have a circuit breaker. It's electrically the same thing, but for what a circuit breaker does, is when whatever it's rated at, in this case it's 25 amp circuit breaker, the rest of the circuit draws more than 25 amps, then if R1, R2, and R3 and R4 all collectively together draw more than 25 amps, that circuit breaker opens. And these you find sometimes in a basement of a house, or in businesses. They're usually in the hallways, and like the one in my house, for example, is in the garage. So there's always circuit breakers or fuses to protect the electrical devices. Okay. All right. So I'm going to try to get this done. Remember, quickly. So what we're going to do is we're going to figure out how much current each device is drawing. How much is R1 drawing? How much is R2 drawing? How much is R3 drawing? How much is R4 drawing? And then we're going to add all four of those together. And I only have a few minutes to do that. All right. And if the total current, let me write this here. So if I total is greater than 25, in this case, 25 amps, then what's going to happen is the circuit breaker will open and it'll shut off power to all these devices. If it's under 25, then it's fine. The circuit will work normally. All right. So what we're doing is we're going to either use the Ohm's law equation to get the current, right? For this first device, that's why I changed it to 45 ohms. For the first device, we know the resistance R1. We know the voltage. We know the voltage on all these devices, right? It's 145. And for the second device, and the third device, and the fourth device, we're going to use the power equation, right? But so current 2 is going to be power 2, which is given to us, divided by the voltage, and that's going to be true for all three of them. And so let's write all these out. All right, so I've done the calculation for each of these. There's the first device is drawing 3.2 amps. The second device, make sure you do this calculation too, is drawing 13.8 amps approximately. The third device, the three light bulbs, are drawing collectively 2.8 amps, and then the last one is drawing 6.8 amps. And so the question is, does this exceed 25 amps? And so when we add all these up, I1 plus I2 plus I3 plus I4, you get 26.6, which is clearly greater than 25. And so this circuit, if it was a circuit breaker, it trips. If it was a fuse, the fuse blows. And so this configuration basically cannot handle. It exceeds 25 amps.